Hello students, this is Professor Chalai, and in this video we're going to look at determination of empirical formulas. As always, you can follow along with our chapter workbooks. Now, by the end of this video, you should be able to derive empirical formulas using masses and derive empirical formulas using percent composition. Let's get into it. Alright, before we get into that, let's look briefly at number 15. So we know that the formula for water is H2O, right? But what does the two for hydrogen and the one for oxygen means? Think about it for a second. Pause the video if you need to, and think about it for a second. Okay, so the 2 and the 1 for oxygen, which we don't actually write because it's implied, doesn't mean that for every 2 grams of hydrogen there's 1 gram of water. It also doesn't mean that for every 2 milliliters of hydrogen there's 1 milliliter of water. What that 2 means is that for every mole of water, there's going to be 2 moles of hydrogen, and the implied 1 here means that for every 1 mole of water, there's 1 mole of oxygen. Really, it means that for every 1 molecule of water, there are 2 atoms of hydrogen and 1 atom of oxygen. A mole is just a more realistically large number of things. So if we are able to find for any compound, for any chemical compound, if we're able to find a number of moles of all of the different elements that make it up, it means that we could come up with a formula for that compound. And that is what we're going to do when we determine empirical formulas. We're going to look at the different elements and see how much moles they have to come up with a formula, specifically the empirical formula for that element. This little chart here is to help you do the math, whether you're starting from the percent mass composition or just the mass of the atoms, how to get the moles and then the mole ratios and then the empirical formulas, and it will come in very useful for you to help solve the following problems. But let's get into an example of one of them. Let's look at number 16. In number 16, we're looking at some compound that has two different elements, nitrogen and oxygen. And it says that the question says that when we could decompose these into their separate atoms or elements, we get 24.5 grams of nitrogen and also 70.0 grams of oxygen. So we separate the nitrogen and oxygen, and we get 24.5 grams of nitrogen and 70.0 grams of oxygen. The question is asking us for the empirical formula for the compound. Now, the empirical formula for this compound will be, it has nitrogen and oxygen, so it'd be nitrogen and some number x that we need to calculate, and oxygen and some number, let's call it y. Now, some of you might be asking, well, why isn't it oxygen and some number x and nitrogen and some number y instead? Well, typically, when we write molecular formulas, we write the elements in alphabetical order for most of them. There are lots of exceptions to every rule that you learn in chemistry, but if you're not sure which order to put the elements in, go alphabetical. Okay, so the compound that we're looking for is N some number x, y, some oxygen, some number y. So let's figure it out. And let's look at nitrogen first. We need to figure out number of moles, right? Because that's what the x's and y's represent, the number of moles of each of the elements. So if we know the mass of a compound, 24.5 grams of nitrogen, we know that we can convert to number of moles using molar mass, right? We look that up in the periodic table, and the molar mass for nitrogen is 14.01 grams per mole, such that the grams cancel out, and in this example we get 1.75 moles of nitrogen. We can do the same for oxygen, right? We start with 70.0 grams. The molar mass of oxygen is 16.00 grams per mole, which means that we end up with 4.38 moles of oxygen. So if we're going to write our formula, we're going to have nitrogen, 1.75 moles, oxygen, 4.38 moles. However, we can't leave the chemical formula like this because we know that we can't have fractional number of atoms in a molecule. We need to have them be written as whole numbers. So one of the ways that we're going to do this is first divide, there we go, by the smallest number. So in this case, the smallest number is 1.75. So if we divide 1.75 by 1.75, We get nitrogen 1, because 1.75 times 1 divided by 1.75 is 1. And oxygen 4.38 divided by 1.75 should give us 2.5. Okay, we get at least one whole number, but the second one is not a whole number, so we need to do something else. Now we need to multiply by small whole numbers. And first you're going to try multiplying it by 2, then you're going to try multiplying by 3 and 4 until you get a whole number in return. So let's do that. Let's first try multiplying everything by 2, right? So n1 times 2 gives us n2. O 2.5 multiplied by 2, so 2.5 multiplied by 2 gives us 5. So now they're both whole numbers, so we can stop there. If this didn't work, we'll go back and try to multiply by 3, or if that didn't work, by 4, and so on until we get whole numbers. But in this case, multiplying everything by 2 works, and so our formula for this is N2O5. So, to reiterate, we first had to find number of moles. As I mentioned earlier in this course, that's always a very good first step. Once we have that, we write what we call here a pseudo formula. It's not the real formula, it's just using the formula. It's a formula using just fractional numbers with decimal places in place of the real formula. We divide by the smallest whole number to make that a whole number, and then we try to multiply by small whole numbers to get everything to be a whole number. All right, you can rewind that to go it over again, but let's try number 17. Pause the video here, try number 17 on your own, and let's see what you get. Okay, in number 17, we do the same type of experiment, and we get 3 different elements this time. We have carbon, hydrogen, and oxygen, and they're looking for the imperial formula. So if we do the whole alphabetical order trick, then our formula should be carbon times some number x, hydrogen times some number y, and oxygen times some number z. So that our formula will look something like this. So let's deal with these one at a time. Let's do carbon. We got a mass of 165 grams. Let's find the number of moles. So the molar mass of carbon is 12.01 grams per mole. So that gives us, for carbon, 13.7 moles. For hydrogen, we started with 27.8 grams of hydrogen. 27.8 grams. The molar mass of hydrogen is 1.01 grams per mole. So that should give us 27.5 moles. And then finally for oxygen, we started with 220.2 grams. The molar mass is 16.00 grams per mole. And so if we do that math, we end up with 13.76 moles. So now that we have the moles for every single element that makes up this compound, we can go ahead and write what we call our pseudo formula. So C, 13.7 moles, H, 27.5 moles, and oxygen, 13.76 moles. They're not whole numbers, so we need to do more. First, you divide by the smallest number. And in this case, 13.7 is the smallest number. So if you divide everything by 13.7, you end up with C1, right? 13.7 divided by 13.7 is 1. H would be 2, right? 27.5 divided by 13.7 is about 2. And O would be 1. Now these all come out to be whole numbers, so we don't need to do anything else. So we could just write CH2O as our answer. Note that whenever we write these, we usually ignore the ones because it's implied. If we have the element there, it means there's at least one of them. So that's our formula for number 17. If you couldn't get it, just send me a message and we can go over where you think you might have gone wrong. Number 18 takes it one step further. We're using mass percent composition instead, but see if you can work it out by yourself. All we need to remember is that we could use fictitious masses. And I'll tell you about that when you after you've tried to work it out on your own. Okay, hopefully you've tried on your own, and hopefully maybe you've gotten it. But let's go this over together. We have another compound with C, H, and O. So let's look at it. Now, instead of giving you the masses, they give you the percent of mass composition. Remember, percent mass composition from a previous lecture just means that if you have a total amount of mass of something, what percent would be carbon, what percent would be hydrogen, what percent would be oxygen. Now, we know that, for example, in our previous questions, we went from mass to number of moles using the molar mass, which was all good. But here we don't have the mass, we have the mass percent. So the easiest trick here is just to assume that you're applying these percentage to some total mass. And to make the math work easier, we can assume that the total mass is just 100 grams. If the total mass is 100 grams, then that means that you have 75.69 grams of carbon. It means that you have 8.80 grams of hydrogen, and it means that you have 15.51 grams of oxygen. So by doing this simple assumption, just assume the total mass is 100 grams, we can easily figure out, get a mass that we can use in the calculation. You could use a different total mass and the problem will come out to be exactly the same, but we're just going to use 100 so that we don't have to figure out what masses these percents are. So let's now go through the same problem now that we have a mass to work with. So for carbon, we're going to assume that we have 75.69 grams. The molar mass of carbon is 12.01 grams per mole. If you're not sure what these are, you'll have to look them up in the periodic table. I've just used them so many times that I've sort of memorized them. So you do that math and you get 6.302 moles of carbon. For hydrogen, we have 8.80 grams. The molar mass is 1.01 grams per mole. And so that comes out to be 8.71 moles of hydrogen. And finally, for oxygen, we have 15.51 grams divided by 16.00 grams per mole to give us number of moles equal to 0.9694 moles. All right, now that we have this, we can go ahead and write our pseudo formula. So C 6.302, H 8.71, and oxygen 0.9694. They're not whole numbers yet, so the first step is to divide by smallest number. When we do that, the smallest number here is 0.9694. So everything divided by 0.9694 comes out to be C 6.5, H 8.98. Now this is so close to the next whole number that we're just going to round this up to 9, and O 1. They're not all whole numbers again, so let's try multiplying everything by small whole numbers. Multiply by small whole numbers. And the first we're going to try is times 2. Let's see if that works. So everything times 2, right? So 6.5 times 2 gives us 13. 9 times 2 gives us 18. And 1 times 2 gives us 2. So everything works out to be a small whole, whole numbers. So we don't need to try anymore. And this is our formula: C13, H18, O2. All right, I hope you got those. If you didn't, just send me a message and we can go over it again together. In our next video, we're going to look at how we can use these empirical formulas to figure out the molecular formula. I'll see you in the next video. Bye.